Welcome to the New Quantum Era, the podcast where we explore breakthrough technologies and the people building the quantum future. I'm Sebastian Haskinger, and in this episode, I'm joined by Thomas Monz, CEO and founder of AQT, or Alpine Quantum Technologies. Thomas has been at the cutting edge of quantum computing from the very beginning of trapped ion technology, with deep roots in both academic research and real-world technology commercialization. AQT has just made their ion trap computer IBEX available on Amazon Bracket, the quantum computing service from AWS. Now, as I've talked about before, I am employed by Amazon Web Services and work in the quantum computing space, but I'm not a member of the Bracket service team. We recorded this episode a few weeks back in anticipation of this launch, and the Bracket team is using some video clips of the episode in its blog. But this is a regular podcast episode in that there's no editorial control other than my own, and the conversation is guided by my own personal interest in these topics. So you will hear in this conversation, Thomas traces his journey from his early days working on quantum networks and high precision measurements in Innsbruck to co-founding AQT to bring robust ion trap quantum computers out of the lab and into both supercomputing centers and onto the cloud. We dive into how AQT bridges fundamental quantum science and practical engineering, what it's like to move quantum systems from research prototypes to commercial devices, and the vital role of error correction and system integration in the quantum stack. We'll cover AQT's new deployments in European supercomputing centers, upcoming availability on Amazon Bracket, and the next steps for scaling up towards truly useful quantum computing. Whether you're a quantum enthusiast, developer, policy watcher, you'll find plenty of insights in Thomas's perspective on collaboration, standards, and what's just over the horizon for this revolutionary technology. Great. Thank you very much for joining me, Thomas. I'm very much looking forward to this conversation. Your work with AQT goes back to the very beginnings of trapped ions as a quantum technology. If you could start just by introducing yourself and talking a little bit about those early days, your sort of transition or journey into the quantum technology industry.
So I started my master's thesis in Innsbruck, initially working on quantum networks. So essentially, it's like, how do I extract a photon from an ion? So you can think of it like a network card for an ion trap quantum computer. That was my master thesis.
Interesting.
And then I did that roughly also the first year of my PhD. But then given the setup of the different groups, I decided to switch over to a different experiment. So then my next year was actually metrology, which means high precision measurements on a particular transition in calcium ions. And then with that background, I then went into quantum info, working on the control of trapped ions, where I then finished my PhD. And I think one part there is like, okay, I did a little bit of postdoc time, but afterwards I was not sure which direction to head. I got an offer from a Scottish laser company. So I then worked for a Scottish laser company for some time, like learning like the sales aspect, customers, campaigns for conferences, how to organize that. Learned a lot from our sales guy there. And then in some sense, the topic came up. Look, in Innsbruck, we've had ion traps. And repetitively, our assistants became professors, moved to other locations, and they always said, it would be cool, it would save me so much time if I could get a trap from you. And so we thought, okay, the university is not allowed to act commercially. And then the question was in the room, can we potentially turn it into a business? Thomas, do you want to turn it into a business? And that was more or less the stepping stone for AQT. And then we said, like, traps is too small. We have to think bigger. And that's where one thing led to another.
So interesting. So initially you were thinking you were going to be almost a vendor, a component supplier to experimental physics labs that wanted to do ion trap experiments. That's really interesting. And so computing is sort of building a system out of the component that you were actually going to bring to market. That's really fascinating. And were you, when you were doing your PhD, obviously, your co-founders are Peter Zoller and Rainer Blatt. So Zoller and Serac are very well known for writing that first paper that sort of hypothesized using trapped ions as qubits, and then Monroe and Wineland experimentally realizing that at NIST. Was that something that was in the back of your mind, sort of the origin story of trapped ions as qubits? Was that something you had been involved in at all?
Well, that was actually my PhD thesis. So to give you a feeling there, the first ideas from Ignacio and from Peter about the so-called Dirac-Zoller gate, we implemented that, and then one of the first projects of my PhD thesis was how can you turn that into a 3-qubit, the so-called Toffoli gate, and the extension towards 3 qubits was part of my PhD thesis, where I say, okay, this is working, but it's not working as good as it should. So we then switched to Möllmer-Sørensen gate and so on and so forth. And then, for instance, just to give you a feeling, it's like I did Shor's algorithm to better understand what goes wrong. So this metrology background was always there in the sense of whenever I do something, can I write down an error budget to understand what were the shortcomings and how do we overcome these shortcomings?
Interesting.
I think this mindset was helping a lot to push the quantum computing forward by always saying, and I think that's the neat thing with ions, is to say it's very pure physics. It's like AMO, it's an ion in vacuum.
Right.
Whatever goes wrong, we can figure out almost on the math level with some characterization. So let's understand what goes wrong. Let's fix it with new ideas. And then we should be able to lower the error rates every couple of years. Right. And I think the ion community, together with Continuum and others, we nicely successfully demonstrated that year and year again.
Yeah, it's impressive. That's interesting. So your academic, your PhD thesis was directly involved in the beginnings of trapped ions as quantum computing, and I think you were involved in the first controlled knot gate operation. Was it? No, that wasn't. Okay.
So this was Malk and others. So I learned from them. Essentially, I would say it's like what the shortcomings were. So like, why is it only, I think in those days we had like 91%, like an error rate of 9%. Nowadays we are at like per mil level. Right. Like, so how the heck 9%, what's wrong there? And then it's like, it's this, we have to fix the B field, we have to get the laser better.
It's so fascinating. I mean, what you're describing, the sort of the error budget and the incremental and continual improvement of the fidelity of ions as a quantum computing platform. It's such an interesting mix of engineering and science. It's sort of deeper understanding of the scientific principles at work. And then applying engineering principles sort of for the greater precision and repeatability of the operations. I'm always struck by how tightly coupled science and engineering are in the field of quantum technology. Is that sort of how you see that as well?
It's very much how I experienced it. To give you a feeling, when I started, we still had a couple of, like, to control laser light fields, you have these AOMs. I still were using some of the old ones because we didn't have so much money in the early days. We had them torn out of old laser printers and just mounted them on because that's why you got AOMs for free. And we mounted them on the tables and used them. And I remember that back in those days, we bought the first optical laser. And as you can imagine, it's like up to that point, we mainly made them on our own. It's like a master's thesis would be to build your own laser. And it's like, but we know how to build it on our own. Why should we give a company money? And then we bought the first one. And then it was like so much more reliable, a good manual. Right. There were improvements that we really said like, no, it makes sense to outsource some of these engineering so that we can focus on the physics again. And so there was a fruitful circle where you say, It's like, let's buy something so I can focus on the physics again. And you see a little bit of the connection for AQT there, where we say it's like, we have these components, like we can accelerate ion physics by giving people ion traps that work, but we can also accelerate quantum information processing by giving people access to good quantum computers.
Right.
To say it's like, you don't have to fiddle around with noise or something special, because it's just good out of the box.
That's really interesting. Yeah, it's always struck me that AQT is still very rooted in the fundamental science. I mean, you're at Innsbruck. You've got very tight relationships with Rainer Blatt, with Peter Zoller, and other active researchers and their groups. And I think even recently you did some work with complete quantum field theory in two-dimensional. It was a simulation of particle physics, or an element of particle physics. Is that right?
Yep. Yeah, well, that's the cool thing. We have, let's put it that way, from a quantum algorithms point of view, there is only a selective small number of algorithms where we really have an exponential benefit from using quantum computers. And so I think we need to support thinking outside the box. And if you think about like HPCs, like the idea is quantum computers will help in some fields of high performance computing devices.
Right.
What are these fields which they are currently used for? Well, many things where quantum plays a role in the first place. It's like chemistry, material science, but also high energy physics. And so if we think about quantum chromodynamics and so on, why not think about quantum devices to use and investigate these problems? And interestingly, it's like, it's not, it's not completely like clear which path will lead forwards in a good fashion. And you could say some of the work, why not go beyond 2 levels? Think about simulations where I use that. It's not a bug, it's a feature. I can directly, more nicely map the underlying physics on a controllable device and then push the field forward.
Interesting. And so, I mean, I always remark on how incredible Feynman's statement in 1981 was that, if you want to simulate nature, nature's not classical, you're going to need a quantum computer. So that's where you're seeing sort of these devices are quantum many-body, by their nature, and therefore you should be able to map quantum problems onto them. That just makes intuitive sense. And that's certainly, as you said, there's only Shor's and HHL and a few other Grovers and a few other isolated algorithms we were aware of that may have sort of abstract applicability, but quantum simulation, we know for certain they're better at that than classical computing. And you just mentioned HPC. That's been a major focus for AQT for quite some time, sort of defining the place for quantum computers in the HPC, the broader classical HPC ecosystem. Is that what motivated sort of the relationship with LRZ and other supercomputing kind of centers?
So for me, it was actually went along those lines. It's because of the proximity to the University of Innsbruck. When we started to think about a quantum computer, I went to the IT department and I said, can I please have a look at the high performance facilities? And they were like, sure, but what do you want to see? And I was like, I don't know yet. I want to get a feeling for the room. And so I went in there, and all I noticed was like many different colors and everything blinking, but everything was constantly in 19-inch boxes. And so I said, if we build something, we have to build something which is compatible with this 19-inch rack standard, because this is the infrastructure that customers are used to.
Right.
I can't just change, let's say, the power plug and say I go for 287 volts. No, it's like we have 220 and so on. And so for us, it was like, okay, let's build it in these 19-inch racks. The very moment we had that, Europe started to say, it's like, if we want to use quantum computers, where would we use them? It's like, and probably it's about computing. We need to bring it closer to computer scientists. What do computer scientists ask for? They usually say, I want to have access to high performance computing. And this could be, yes, there are facilities from Amazon where I can get access to AWS and so on, but some of them are more on site. And so for us, there was really like a way of saying, okay, if this is what people are used to, lower the entrance barrier. If they can access HPC, ideally, you can envision it like, how do they don't want to know? Think about your laptop. It's like you might not care. Is it an Intel, an AMD, whatever chip is in there? You could say, I want to run something on an HPC facility, whether it offloads some task to a quantum accelerator in one corner of the HPC center. I don't care as long as it's faster and better. And that was this idea of let's bring it into HPC because this hybrid infrastructure is something that the customers want. They don't want to know the details that should be behind the API. And the library takes care of the different hardware, but it should just work.
Right. I mean, that's such a critical stage in the transition from scientific research to deployed technology, is that abstraction and allowing the end user to use the device for a purpose of their own without caring about, tuning the lasers and the optical table and all the rest of the idiosyncrasies that are required for the scientific research. I mean, that level of control, that sort of intimate knowledge of how it's operating is exactly the focus of scientific research, and it doesn't really have a place in technology. So was the deployment of the first device? I think the form factor is PINE is your acronym, right? For the form factor. Was that at the University of Innsbruck or LRZ?
No. So the first system was deployed as historically, it's like we set some up in the very first office, which was like on university grounds. And the first thing we learned about stability is when we moved to this office, which I'm currently in, which forced us to move it a couple of 100 meters, but it doesn't matter whether it's 100 meters or 100 kilometers, because we had to put this box into a truck, move it across the building, get it out, get it down the stairwell. And so the first time we did it with a customer, as you said, was LRZ in Munich. And that went really, really smooth. And then very swiftly afterwards, we actually got the second system installed in Poznan in Poland. And then we just built the system, get it on a truck, drove to Poland, and that's it.
And that Poznan, that's the EuroHPC center, which is part of the EU's effort to deploy, I think, 6 or so different devices in different EuroHPC centers, right?
So I think by now it's 12 because they broadened the scope. So initially it was more quantum computing focused, but now on purpose also includes quantum simulators. It makes sense because you could say I'm a computer scientist. There are different devices, different ways of controlling them, depending on which problem I have. What's the ideal, solution, chip or platform to solve it? And for some of them, you'd say maybe a digital device is not the right way forward. Maybe you want to do boson sampling or something. So if I have access to more, it's only benefiting, in that case, a European customer base.
Yeah. So the deployment at LRZ in Germany, that's part of the Munich Quantum Valley, which involves TU Munich, and there's been quite a bit of work in looking at sort of what are the challenges and how can they be systematized for integrating quantum computing with classical HPC. Was that something that AQT was involved in as well?
So partially, it's like we said we want to focus on the computer per se. The hardware inside, we want to make the quantum computer work, and then we'll happily go up to the level of the API. And then it depends a lot. That's also what we learned from discussing with HPC people, which I think many people in the HPC domain are aware of. Like everyone has his own or her own ideas on how to do a scheduling task, like how to distribute the workload. And so we noticed it will be hard for us to say it's like this is the right way forward because they have already pretty good ideas on what they think is best given their infrastructure. And so we said we'll go up to the level of the API. We'll help you with integrating at that level. How you want to integrate it in detail, That's something we leave up to you. For instance, Martin Schulz and Robert Wille are doing really, really great work there on how to integrate like different platforms in a heterogeneous structure into HPC with quantum. And I'd say it's like, if you want to extend the podcast, Robert would be really cool, like contact and partner to having this discussion on how to bring that on board.
Yeah, absolutely. Absolutely. And so, I mean, that's a really interesting sort of, as you said, lessons, many powerful lessons can be drawn from all those experiences in deploying and integrating quantum computers with classical computers. How do you see, now you're bringing AQT to the Amazon Bracket service on AWS. How do you see the lessons that you've learned with on-premise deployments in relation to sort of deployment in the hyperscaling cloud?
So for us, I think having this API and saying this is how far we need to go and being willing to say like everything beyond we leave to the partner is very much similar to what we have to do as we work with Bracket. We say it's like, here is the handover point. You take care of your part, we take care of our part. It helped us a lot to have, say, on the API level, like certain numbers, characteristica available so that, let's say in that case, Bracket can extract meaningful information. That was already there. Like all the monitoring capabilities have already been developed in the context of HPC and are now adapted for Bracket. So the overhead was notably, I wouldn't say it was nothing, but there was a reasonable good foundation to build on top.
That's excellent. And are there opportunities for collaboration or experimentation that you think a global cloud provides that are different from those on-premise deployments?
I think the cloud has a notably broader width of customer requests. It's like it could be commercial customers that say, I want to have a special feature, and this is like a very technical feature, but it's very well founded on economic reasons. And you could have a very cool, interesting idea from scientific people, but more along the lines of, I want to try something out, and having this feature would make my life easier. And so I'd say in HPC, the focus is notably tends to be, from what we saw so far, notably more scientific and academic.
Right.
Which is fine. I think we will learn a lot about the more commercial, ways people think about quantum computing.
Right.
It's not about how they use it, but it's also what the expectations are on what it should do, or what information should be available, or how it should react, which is a little bit different, and I'm really happy to learn.
Interesting. Yeah, that makes sense, because supercomputing centers tend to be in the U.S. Of course, they're typically operated by Department of Energy, for example, and they're primarily focused on scientific computing as their main area of activity. So that makes sense, and the cloud is clearly motivated by that's where businesses run their IT is in the cloud. So it's much more commercial in nature. Do you foresee sort of the presence on the global cloud being something that helps accelerate your plans for your roadmap towards fault-tolerant quantum computing and scalability? Is that it's sort of the agenda at this point?
So it's the revenue for sure will help. No, but I think one technical aspect really is end users. It's like they want to benefit from error correction, but they don't want to do error correction. And I think in that sense, it will be interesting to talk with various parties to say, is there someone who says, is like, here is this, let's call it 3-qubit problem, but how do I map the 3-qubit problem onto a 3-logical qubit problem with encoding, decoding, and so on?
Right.
Is that going to be a service that's like maybe part of Bracket, maybe part of a third party? How do we make sure that this solutions, like say, how do we integrate them in this entire chain? So that it's like, say, if you would be the end customer, you say, I don't care what you have to do, just do this thing. And at the end of the day, don't tell me that you had 300 qubits for your logical solution because I gave you a 3-qubit task. I want a 3-qubit answer.
Yeah.
And in that sense, I think broadening also with our services, broadening the playground for instance, software developers, like quantum software, quantum service developers, and saying there is an additional system. We might be more approachable to compared to others to say, it's like, can you add a certain feature? And we'd say, it's like, we're working on that anyway. We do a beta, something custom access. We give you this custom feature and we say, this feels like it's going the right direction. Let's do a little bit more. And then you'd say we can offer something cool, convenient, nicely, fully integrated with Bracket, which makes the life of end users easier and they benefit from higher performance with no extra complexity. I think if we can enable that, like with our hardware, but with the broader quantum ecosystem, and this is something we want to push for because it's like everyone will benefit from that. Then we are moving in the right direction.
Yeah, I mean, you've already had an active partnership with Classique, I know, and they're, they are another partner of the Bracket service. They use Bracket as a way to access hardware. And I think you're right. I mean, I think the exciting thing about watching the hardware companies, the software companies sort of using Bracket as sort of the GM Bracket used to call it the town square for the quantum industry. Everything, all the interactions benefit everyone actually, as we work out, how to actually get this stuff to the point where it has commercial value for our collective customers. Is there, you mentioned error correction, is there a scheme that AQT sort of favors in terms of error correction, given the characteristics of your platform?
So I think that's the huge benefit of trapped ions in the first place, that, okay, shuttling has its drawbacks, but at least we can relatively easily get long-range interactions in the platform. And this allows us to be very, very agnostic to codes. And if you think about my own history, I think it was still part of my PhD thesis together with Philip, where we did the normal 3-qubit repetition code. And then it was Markus Müller, who is now in Jülich, who said, like, no, you need to think about topological codes. And so we started working on color code and Steen error correction and so on. And nowadays, people are leaning heavily towards LDPC codes, which have, again, like these long-range interactions, which are something neat and how to say native to trapped ions. But it's also been amazing to see like the changes which took like a few years only. If you think about, it's like we had the surface code and the nice results from Google with larger code distances. And it feels like almost the entire, like a large amount of the community has switched to LDPC within a year or so. And I think if the next person stumbles upon an even better solution, 2-3 years, I think for us with ions, we don't have to change the chips each and every time.
That's interesting. Yeah.
We can have a, let's say more software-enabled robust platform where changes to the encoding doesn't necessarily mean we have to start from scratch to build a new trap.
Yeah, interesting. And you mentioned shuttling. So I think the question that the ion traps are all faced with is what is the answer to scaling up beyond a single trap? And there are some approaches that, like the racetrack at Quantinuum, and others. What's the AQT strategy for getting to sort of those hundreds or thousands or even beyond in terms of numbers of qubits?
So the traps per se, I mean, the first goal needs to be 2D. It's like the essentially the number of shuttling operation depends on how many dimensions you have available in your trap. Rule of thumb. There are some prefactors, but you could say instead of a linear string, if I have something 2D, it's only square root, and if you go 3D, it's the third root, and so on. This is something which we push for, carefully selecting in that sense also how much overhead do I have to deal with. Can I get, say, all the control inside? Like how many interaction zones do I have? It doesn't help if I have, let's say I have 1 million ions, but if I have only one interaction zone, so I need integrated photonics, and we have activities along those lines, because in particular in Europe there has been this CHIPS Act now, which allows us to work with various partners to do integrated photonics, waveguides, and so on. But I think on the long run, similar to what we are doing here, is like we have to think about how do we interface quantum computers, not just within a chip and make it larger, but what like Rainer used to say is like there is scaling down. So like we have to make structure smaller. There is scaling up, which means control larger and larger system size, but you also have to think about scaling out. So what do I do if I have, let's say, HPC and clusters? I have 2 computers. I need this network cable. With ions, I think it's really neat because it's controlled to a large degree already with light, and we can get light out. And we have already demonstrated in Innsbruck, like remote entanglement between ion traps across the campus. And so in that sense, being able to say it's not just like, say, within the same room, but we in principle can also send it over larger distances, even telecom compatible. That makes trapped ions a really, really interesting platform, which essentially other platforms are struggling with.
Right. It's a little bit easier than transduction in a superconducting regime, for example. So you mentioned 2 dimensions. How do you plan to realize a 2-dimensional trap? Because normally, I mean, the optical trap is just a 1D sort of array, right?
So no, that's no problem. So like building a junction, for instance, colleagues in Mainz have already been working on that. Colleagues in the UK have been doing that. So like you can have junctions, you can move left, right, up, down. It will be more of a question, I think, like which is easy to overlook. One part is like controlling the ions, yes, but how do I do all the multiplexing and so on? That if I have 1 million segments, I can't bring 1 million cables inside. And I think that's a nice connection to what we said in the beginning. It's like, you can build your own diode laser. But you want to, if you buy it, you can focus on the physics again. And so if you now say it's like, I have partners which give me the multiplexing capabilities, which give me the integrated photonics and integrated light control, then I can focus on the quantum processor again. And now you see it's like there are different building blocks that you have to fix and make available to the community in order to scale up and tackle the problems which are on the quantum side and not so much necessarily on the classical control side.
I see. Interesting. So you're right on the verge of deploying on Amazon Bracket. By the time this podcast is out, you will be on Amazon Bracket. Beyond that deployment, there's obviously going to be, an initial phase of sort of settling into that. What do you see as sort of the next major, objectives or goals for AQT in the coming year or two?
So I think the key part is we have to, AQT, but the community as a whole, we have to provide better quantum computers which offer like a benefit for end users. I think as long as we stay in this, it's, let's say, scientifically, technologically interesting, it's nice. But if we want to unlock economic value and an actual market, we have to build devices where people say it's like it's better to use this quantum device compared to using a classical device. And I think there the advantage for us with ions is because we have lower error rates, the overhead on how large the system actually have to be can be significantly smaller. And this is something that we are pushing for.
Really interesting. That's fantastic. Well, Thomas, thank you very much for your time. This has been really interesting, and I'm very much looking forward to seeing, what uses people find for the AQT hardware on the Amazon Bracket service.
Thank you.
Thank you for listening to another episode of the podcast, a production of the New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by OCH. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.